Okay, so hopefully you were able to work on that. So I went back up and said, hey, x of s is y of s times 4 minus x and then all minus 6. Remembering that y of s was this guy, substituting that in and then subtracting 6. But to subtract fractions, we need a common denominator. So I get a common denominator and then I simplify, which leaves me with x of s is equal to this guy, which I can then break down using partial fractions and then find out using the inverse Laplace transform that x of t is 13 thirds e to the 5t minus 10 thirds e to the 2t. And remembering what y of t was, it was 13 thirds e to the 5t minus 5 thirds e to the 2t. And just as a quick check, let me pause that. Let's see, we've got, this should have been a negative. Oh yeah, that's right, because when we came up here, when I put in the 5, I said negative 13, but only wrote 13. So that should be negative 13 thirds. So negative 13 thirds. So what did I do to catch my error? I remembered that my initial condition was y of 0 equals negative 6. So if I stick a 0 in for t, this whole thing should come out to be negative 6, and negative 13 thirds minus 5 thirds is negative 18 thirds, or negative 6. So just because you can easily make a mistake, it's not a bad idea to double check your initial conditions. Let's see, x of 0 would be 13 thirds minus 10 thirds, which is 3 thirds or 1, and so that matches. All right, so yeah, so you can do a quick double check just to make sure that you didn't blow a sign somewhere along the way. Okay, and lastly here, we want to talk about how you can use another theorem from this section to help find the inverse Laplace transform, but now without having to do partial fractions. So sometimes we have somebody of the form L, or the inverse Laplace transform of f of s over s. So we have some Laplace function that we know, but divided by s, and we can convert that into an integral from 0 to t of f of tau d tau. So let's look at an example here. If we have our capital F of s is 1 over s times s squared plus 9, we can then say, hey, that our inverse Laplace transform is going to be the inverse, our function is going to be the inverse Laplace transform of this guy. But I can think of this as 1 over s squared plus 9 over s, using just some algebra here. And so that's going to be the inverse Laplace transform of, or sorry, the integral of the inverse Laplace transform of this guy, which is this guy right here, which we recognize if I were to times by a 3 and divide by a 3, we recognize this guy as sine of 3t, okay? But we need the 1/3, so that 1/3 can factor out front. Oop, and so I almost forgot that 1/3. So there he is. And so we get 1/3 integral from 0 to t of whatever this Laplace, inverse Laplace transform is. And that guy is sine of 3 tau d tau. But my t's and tau's look a lot alike. So this would be the integral of 0 to t of sine of 3x dx, if you want to use a more common letter. And we can then do, we get the integral of this. Let's find out. So we've got 1/3. The antiderivative of sine of 3x is negative cosine of 3x over 3. And we're going to evaluate that from 0 to t. And if we do that, we're going to get, let's see, I'll pull the negative 1/3 out here with this guy, call it negative 1/9 cosine of 3t minus When I stick a 0 in, I get 1. And so our function should be this guy right here. And we can finish this guy up. Oh, I bumped the paper here. So we notice that this guy, f of s, we could then find out what his inverse Laplace transform is. Okay, and noticing that this guy would then be the, we could look at him as the inverse Laplace transform for 1 over s times s squared plus 9 over s, which would then be the integral from 0 to t of this inverse Laplace transform, which we found out just a minute ago, would be this guy, but so that we don't mix up our variables, let me go ahead and just call this guy negative 1/9 cosine of 3t plus 1/9, just so he's a little easier. And so instead of, we can use tau for our variable, we can use x. So this guy's going to be the integral from 0 to t of this guy, but I'll use the dummy variable x. So negative 1/9 cosine of 3x plus 1/9 dx. Okay. So we're just using this fact again. And so if we do that, we're going to get negative 1/27 sine of 3x plus 1/9 x taken from 0 to t, which would give me negative 1/27 sine of 3t plus 1/9 t minus 0 plus 0. So we would just get negative 1/27 sine of 3t plus 1/9 t. Now, if you wanted to, you could take and break this apart into partial fractions. Here, we'll teach you how to handle the repeated roots shortly, though. So hopefully that's made sense. It's another way that you can find the inverse Laplace transform, but in this case, we did it without having to do the partial fractions.